Hunter, and this is the final live stream for general chemistry students, 221 for the fall term. Um, Today we're going over bond and molecular polarity. The original assignment on here was a little bit heavy on Lewis structures. Hopefully, because of uh, the most recent content, you should be pretty solid on that. Now we're going to be going in a little more depth. And I do want to apologize in advance. Normally I would have a little bit more time to prepare for these. I had my anatomy practical yesterday and was preparing for that. And so you're going to get to see a little bit more of my process as we go through this. And I will be referring back to my notes from when I was in 221 a few years ago, because I want to make sure that I don't lead you astray here. I want to give you the correct information. So with that, we're going to get into the exercises. We're going to start with 44A. And I've set up a little bit. I've set our work up here a little bit so that we can kind of get through this first one. Come on now. So write resonance forms that describe the distribution of electrons in each of these molecules or ions. And we're starting with selenium dioxide, that is SeO2. I'm going to go ahead and draw this as written because there's some structure implied in how it's written. Right? We don't have O2, we have the oxygens separated from each other. Now we know selenium has, I'm going to make these a little clearer, 6 valence electrons. I'm going to make a leap and say that those lone pairs are not tied up with the oxygens. And we know each of these oxygens also has 6, 2, 4, 6 valence electrons. And so just to get started here, I'm going to draw these, so I'm going to get that a little more precise, with a single bond in between. Spoiler alert, this is wrong, right? The oxygens are not going to be happy in this configuration, and we can prove that, or we can demonstrate that by calculating the formal charge. So to get started, we would calculate first the number of electrons that we're dealing with. This is our accounting step, just to make sure that everything's copacetic. So we have 1 times 6 valence electrons for selenium and 2 times 6 valence electrons from the oxygens. That gives us 18 total electrons that we have to account for. Right now we have 4 of those tied up in electrons, which means that we should have, is that right? 14 lone electrons. 1, 2, 3, 4, 5. Yes, I'm going to count that simply. 6, 7, 8, 9, 10, 11, 12, 13, 14. All of our electrons are accounted for. Minus 14 equals 0. So everything's accounted for right now. Now we have to calculate our formal charges to test whether we're on the right track. All right, so first we're going to do selenium. And our formula is formal charge equals the number of valence electrons that we started with, that's 6, minus lone electrons. On selenium right now we have 4, minus the number of bonds, and here we have 2. 6 minus 4 minus 2 equals 0. Okay, so selenium's happy like this. That's great. How about our oxygens? We started with 6 minus 5 minus 1 equals 0. And I'm second guessing myself because I don't believe that this is the correct resonance structure, or it ought not be. Let me backtrack here a little bit. Yeah, okay. Oh, oh, well, that's easy. Can't have a single electron hanging by itself. We need these lone pairs. They don't want to hang out like that. So I want to find in the textbook what the rule is for this really quick, because that explanation cannot stand on its own. That's not satisfactory. So, standby, formal charges and resonance. We calculated formal charge, that's fine. Let me correct this really quick. So if we have, for example, 6 and 1 would give us -1. But if we have 6 and 4 and 2 equals 0. Okay, although I'm not satisfied with that explanation, I think we simply have to leave it with I made a very, very simple error early on, and that is that we cannot simply have 5 lone electrons hanging out. They need to be in pairs, so 4 or 6, as the case may be. And just to do my accounting, we started with 18 valence electrons. I'm going to do this in red again. Minus 2, 4, 6 in bonds gives us 12. Minus 2, 4, 6, 8, 10, 12. That's not right. 2, 4, 6. That's not right. Minus 6 in bonds would give us 12. Yeah. Minus 2, 4, 6, 8, 10, 12. That would be 14. Where I've obviously made a mistake. And as I said, I don't want to leave you astray. So I'm going to go back through here and figure out where the error is here. Because that cannot stand. Oh. I had an extra lone pair on selenium, uh, which I did not account for when I added the bond here. So, okay. We made our mistake right at the beginning, and then we compounded our mistake when we tried to catch ourselves later. 2, 4, 6, 8, 10, 12. Now all of our electrons are accounted for. 1 and -1. Okay. And we need to add that we have a negative charge on that oxygen because we have that negative formal charge, and that shows up as an extra electron in that lone pair that is not participating in bonding. Now, for resonance, I'm going to redraw this. We have our lone pair on selenium. We have our lone pair here and here, and I'm going to do this in red. The resonance structure, basically these electrons in red, back on the original one that I drew, can start participating in bonding, and these electrons will jump up and hang out on the other oxygen. And our resonance looks like, oh, let me make sure I get that. like so. So these are our resonance structures. Because this is a because this is a fairly symmetrical appearing um, molecule that just appears to mirror each other. But also looking at this, you should note that we have a couple areas of electron density around selenium. And so this would not be a linear molecule, right? This would have a bent configuration because you have one, two, three areas of electron density around that selenium. Okay. That was a little roundabout. So let's see if we can clean that up for our second example here. Oh, come on now. There we go. All right. We start out by calculating the number of electrons. We have carbon, oxygen, and hydrogen. Carbon has 4 valence electrons, oxygen has 6, hydrogen has 1. We have 2 oxygens, so 2 times 6 is 12. Sum those together, 12 plus 4 is 16, plus 1 is 17. So 17 total electrons that we have to deal with. We can see that 2, 4, 6 appear to be participating in bonding, and we have a negative charge on this. So real quick, we have 18 total electrons to account for. Okay. It appears that we have 6 bonding electrons, gets us down to 12. And now we have to account for those as lone pairs. So we could just draw them here around our oxygens, but 2, 4, 6, 8, yeah, that would work in terms of having a full octet around them, but we don't have any around carbon here. We're missing electrons. Electrons are unaccounted for, so that's not going to work. So let's try. We fill carbon's octet. It's happy now. So there's 2. We have 10 more to account for. If I put 2, yeah, let's start there. If I put 2 on this vertical oxygen, this north one, we have to account for some more in that bond to fill that octet. So that's minus 4 as lone pairs, minus 2 additional as a bond. Oop. Gives us 4 left to account for. All right. No. We did that double bond. Accounts for the lone pair that would have been on carbon. Lets us get rid of that. Now we have them all accounted for. So let's back up. We had 12 that we had to account for. We've got 2, 4, 6, 8, 10 as lone pairs. Left us with 2. We put that into a bond. That's all of our electrons. Okay, let's check our formal charges. And again, we know from the previous problem that because we have this extra lone pair on this right-hand oxygen, that it's going to have the negative charge assigned to it. That's already accounted for up here. So I'm not going to draw it in there yet. Actually, you know what, I will. I'm going to put it right there, just in a different color. Got to check our formal charges. We've got carbon, oxygen, hydrogen. Hydrogen just has the one electron to play with, so that's should be pretty easy. Carbon, we start with 4 minus 0 minus 2, 4, 6, 8. Wait, 4 bonds. Not number of electrons, number of bonds. Equals a formal charge of 0. Oxygen, we start with 6 valence electrons, minus, we'll start with, this will be oxygen A, this will be oxygen B. Oxygen A, we've got 4 lone electrons and 2 bonds. 0, that's a super happy oxygen. We'll just do B right here. So that's A, here's B. We've got 6 minus 6 minus 1 gives us a -1 charge. Hydrogen's easy. So our -1 charge is accounted for. One of those oxygens has an extra electron assigned to it that is not participating in bonding. And our resonance structure would simply be one of these electrons coming down here and playing in bonding, and one popping up here. And so our other resonance structure, oof, keep starting this backwards. There's my puppy in the background. Looks like so. Okay. Hopefully that was clear enough. Cool. Let me check on. All right. Cool. I'm satisfied with that. Moving on. Question 51. Determine the formal charge of each element in the following. And we're just doing B and D. All right. So carbon tetrafluorine. Pull up my periodic table here. Determine the formal charge of each element in the following. So we could just skip to calculating formal charge, but let's go ahead and draw our Lewis structure just to be thorough here. We know that carbon has 4, and each fluorine has 7 valence electrons. Gives us 32 total electrons to account for. Carbon already has a full octet, so we're not going to put anything on there. It's also not hypervalent. So the remaining electrons all have to go on the fluorines. Six times, oh, make sure I get this going first. -24 minus should be 24, which gives us 0. Cool. So all of our electrons are accounted for. Now we can move on to formal charge. So formal charge calculation. Well, okay. Formal charge. Carbon, we started with 4 valence electrons, minus lone pair electrons, we have 0, and number of bonds is 4, equals a formal charge of 0. Fluorines, we started with 7, minus 2, 4, 6 valence electrons, and 1 bond, gives us a formal charge of 0, this one's happy. We don't have to change anything about it. There's no resonance structure to worry about, no double bonds we have to figure out. It's good as is. Easy peasy. Let's look at phosphorus pentafluoride. Oh, excuse me. There's 1, 2, 3, 4, and 5. Phosphorus is in group 3 or above, so it can be hypervalent, which would have to have 5 bonds in the first place, right? So let's look at number of electrons again. We've got 5 times 7 valence electrons for fluorine and 5 for phosphorus. Gives us 40 total to worry about. If we assume that all of these are single bonds, 2, 4, 6, 8, 10 are accounted for, and we have 30 left that we need to account for. Again, to fill each fluorine's octet, we would assign 6 lone electrons in pairs, and 5 times 6, because we've got 5 of them, would be 30, and that would account for all of our electrons in this molecule. So let's look at formal charge. Phosphorus, we started with 5. We have no lone electrons, and we have 5 bonds. Formal charge on phosphorus is 0. Each fluorine, we start with 7. We've got 6 lone electrons minus 1 bond each is also 0. And because I want to be thorough again, I'm going to check my answer key here. And come on now. Where's my answer key? May have closed the window that I need. That's fine. We're on 51. D. Yes, we should end up with a formal charge on each of 0. So that is correct. And the same for B. Cool. Feel pretty secure in that. Next up, we're 52, A, B, and D. Okay. Determine the formal charge of each element in the following. So same exercise, but now we need to pay attention because we have charges, positive and negative charges assigned to each of these molecules. That is going to change the distribution of electrons, obviously. It's also going to change the number of electrons that we need to account for. So this initial accounting step is still important. All right. Oxygen and hydrogen. Gives us 9 total electrons that we need to account for. We got rid of 1 because we have that positive charge. So we have 8. 8 that we need to account for. Oxygen is the most electronegative atom. It's going to be located centrally. Each of those hydrogens can really only participate in 1 bond. So that should be kind of a spoiler. There are going to be no double bonds in this, which means the rest of this is just where we put lone pairs. So after accounting for those 6 electrons, involved in bonding, we would have 2 electrons left which could only go on that oxygen and fill oxygen's octet. So let's calculate our formal charge for oxygen and hydrogen. Oxygen, we start with 6. We have 2 lone electrons and 3 bonds. Gives us a formal charge of 1. Each hydrogen has a formal charge of 0. Our positive charge is accounted for. All of the electrons are accounted for. Those are our formal charges. So that was for A. Let's look at B. We have sulfur. Let's draw this first. Sulfur with 4 oxygens. We have a 2 negative charge. Okay, we'll come back for those electrons. Let's calculate the number of electrons first. Sulfur has 6. Each of those 4 oxygens has 6. 24 plus 6 is 28. Total electrons plus 2 lone electrons gives us 30 that we need to account for. Okay. If we just have single bonds, 2, 4, 6, 8, gives us 28 that we need to account for. Can we account for all of those by putting them 6, 12, 18, 24? We cannot. We cannot put all of those on the oxygens and call it good, except, yes, we can, because sulfur is in group 3 or above, and it can be hypervalent. So let's try that. 2, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28. Now, to see if this will stand, we have to look at our formal charges. We started with 6. We have 4 lone electrons and 4 bonds. Gives us a formal charge of -2. Each oxygen started with 6, has 6 lone electrons and 1 bond. Gives us -1 on each of those, which would give us an overall 1, 2, 3, 4, 5, 6, which would give us an overall -6. Excuse me, 4 times 4. Which would give us an overall -6 charge on this molecule, which we don't have, so this is incorrect. This cannot be correct. So we like the lone pairs on sulfur. So how do we want to deal with this? Let's see. Come on. Okay. Since we've done the previous exercises, you may have looked at this Lewis structure that I drew and gone, oh, if we have a single bond on an oxygen and 6 lone electrons around it, we know that each of those is going to have a negative charge. And if you're good at pattern recognition and you noticed that early, fantastic. So how would we deal with that? We would get rid of some of these lone pairs, and we would get rid of the lone pairs around sulfur as well. and those would participate in bonding. Okay. Now, our negative charge is localized around the oxygens that have extra lone pairs. Okay. Let me scroll this up a little bit so that you can see. So let's try with this new configuration. We have 6 minus 0 minus 2, 4. Sorry, 1, 2, 3, 4, 5, 6 bonds equals 0. So sulfur's resolved. We have two different, I need to do this correctly. We have A and B. Oxygen A has 4 lone electrons around it and 2 bonds, gives us a formal charge of 0. Oxygen B has 6 lone electrons and 1 bond, gives us a formal charge of -1. We have 2 of them, gives us a formal charge of the overall of the molecule of -2, which matches with the charge on the molecule that we were given in the prompt. I feel pretty comfortable leaving this question here. I think that about covers it. It's so important to do the accounting steps in these until you can recognize these patterns more fluently. Once you get into organic chemistry, you'll be doing this so much that you can pretty much do it in your head. I'm actually tripping over myself a little bit because I'm having to write out the accounting process. Um, and I haven't, it's been different for a while. So moving on, let's take a look at 53. We're going to calculate the formal charge of chlorine in 3 different molecules. We have chlorine with chlorine. So for number of electrons, 14 total. Chlorine bound with chlorine. If we just throw a bond in there and fill an octet, that gives us 2 participating in bonding, gives us 12, minus 6 times 2 is 0. That looks okay. Formal charge of chlorine started with 7. We have 6 lone electrons around it and 1 bond. Formal charge is 0. All right, that's our first one. Let's look at, is that beryllium dichloride? Be, where are you? Beryllium. Okay. Beryllium has 2 valence electrons to play with, and each chlorine has 7. So we have 16 total to account for. Let's just try this. Fill some octets. Let's see where we're at just with 4 electrons participating in bonding. Gives us 12. Minus 2 times 6 is 12. That's all of our electrons accounted for, but we have empty space in this beryllium, so that's not happy. That would be very sad. Calculate the formal charge of chlorine in the molecules. Well, if we're just calculating the formal charge of the chlorines, they might be just fine. because if we calculate our formal charge of chlorine, we had 7. We have 6 lone electrons and 1 bond. That's 0. That would get us our answer. But beryllium would be hmm. Beryllium would be sad because it would have an unfilled octet. Hang on. Do we care? Are we worried about that? I'm gonna have to scrape the inside of my brain for a minute. Actually, I'm not gonna make you do that. I'm gonna go back through my notes and see if it just happens to be an example that we went over. Yeah. Let's see. That's polarity. We're not quite there yet. We're kind of, but we're still on formal charge. Formal charges in resonance. Are we content to have hypovalent? Doesn't show up. Beryllium often has only 4 valence electrons. Beryllium is a notable exception. This is this is kind of satisfying to me. Um, I could not have remembered that without checking my notes, and I'm really glad we did. So there are exceptions to the octet rule. Um, Electron deficient molecules have a central atom that has an unfilled valence shell. Beryllium often only has 4, and boron often has only 6 valence electrons. And there you have it. I am satisfied with this answer. Cool. Let's do the last one, which is chlorine pentafluoride. Fluoride? Fluorine. Doing our accounting. 1 times 7 and 5 times 7. 42. Okay. Chlorine in the center. 1, 2, 3, 4, 5 fluorines. 2 times 5 gives us 10 participating in bonding. Let's see. 5 times 6 would only give us 30 if we did all lone pairs, which means that chlorine would have to have an extra lone pair on it, which it can because it's in group 3 or above, which we could infer because there are 5 fluorines bound to it. So that's all of our electrons accounted for. Fantastic. Love that. Don't have to think about it anymore. I'm going to go ahead and draw our 6 electrons on each fluorine, just for good measure, in case we have to mess with them. Let's do our formal charges. We've got chlorine and fluorine. Chlorine, we started with 7. We have 2 lone electrons and 5 bonds. Gives us a Formal charge of 0, amazing. Each fluorine has 6 lone electrons and 1 bond, giving us a formal charge of 0. And according to our answer key, that is a perfectly acceptable answer. All right, 56. Based on formal charge considerations, which of the following would likely be the correct arrangement of atoms in nitrosyl chloride? ClNO or ClON? Ooh, interesting. Okay, based on formal charge considerations. Let's try this one. So again, pattern recognition. We know that chlorine is going to be happy from a formal charge consideration. It's going to be perfectly happy with 6 electrons floating around it in pairs, and 1 bond would give it a formal charge of 0. We also know that oxygen would not be happy in the same configuration. But if we had 4, so 2 lone pairs, and a double bond, that it would be happy. So how would nitrogen be? Well, first, we ought to have calculated the total number of electrons that we were dealing with. Would give us 11, 18. 2, 4, 6 gives us 12. Okay, that's all of our electrons accounted for. I'll actually do the math for you. 2, 4, 6 involved in bonding gives us 12. 2, 4, 6, 8, 10, 12 as lone pairs gives us 0. That's all of our electrons accounted for. All right, nitrogen, we started with 5 valence electrons. We have 2 as a lone pair, and 3 bonds gives us a formal charge of 0. We could stop here. We could stop here and say this molecule on the left, chlorine to nitrogen, nitrogen to oxygen, is likely the correct arrangement based on a formal charge consideration alone. Let's go ahead and do the exercise since we're here and we have time. Do we have time? We don't really have time. We have 17 minutes and I have a lot that I want to go through. So we're going to move on to the next one. And for question 60, actually, which ones did we need to do? It just says question 60. So we'll pick 1 or 2 from here. Iodine forms a series of fluorides. Listed here. Write Lewis structures for each of the 4 compounds and determine the formal charge of the iodine atom in each molecule. All right, we'll start with A. We have iodine and fluorine. Iodine has 7 valence electrons, as does fluorine. And so, if you're good at pattern recognition, that one should be pretty straightforward. Let's look at iodine trifluoride. That would give us, so I'm doing the number of electrons in my head, but I should do that. 28 total. Minus, we'll start with 6, gives us 22, minus, is that right? Yep, minus 18, gives us 4. Iodine is at or above group 3, so it can be hypervalent. That's fine. Let's look at our formal charges. We know what fluorines are. Those are 0 right now. But iodine would have a formal charge of 7 minus 4 lone electrons minus 3 bonds. 4, 5, 6, 7 equals 0. Cool. Keep boxes around these to keep them straight. We'll do one more. Let's do, well, again, if we're good at pattern recognition, we can do this without drawing it. So let's try C, and let's see if we can try our formal charges. Let's assume that it's 5 single bonds to each of those fluorines. No, we can't do that, can we? Yeah, we can't do that because we don't know. We can do this without drawing it. We shouldn't, but we can try. Start with our number of electrons. Iodine has 7. 5 times 7 is 35, plus 7 is 42 total. We have 10 participating in bonding is 32, minus 5 times 6 is 30, gives us 2. So the iodine, as we're calculating formal charge, start with 7, could have those 2 lone electrons around it, and then 5 single bonds, and have a formal charge of 0 on it. Cool. I think you guys get the idea. I hope. I'm going to move on to the next problem. Predict the electron pair geometry. Ah, yes, shapes. Three-dimensional shapes, my favorite. And the molecular structure of each of the following molecules or ions. Okay. I'm so excited. Let's see. Okay. Ha! Sulfur, hexa, fluoride, sulfur. Number of valence electrons is 6. Fluorine, we have 6 times 7. Oh my goodness. This is going to be awesome. 48 total. If we assume that each of those fluorines is participating in a single bond, which they would be, we have 6 times 2 is 12 accounted for, gives us 36 to account for. Yep. And then 6 times 6 is 36, because we do have lone electrons around them. Minus 36 is 0. So we would just have a sulfur surrounded. Is that right? Let's check our formal charge. 6 minus 0 minus 6 equals 0. 7 minus 6 minus 1 equals 0. That would work. Predict the electron pair geometry and the molecular structure of each of the following molecules or ions. Sulfur hexafluoride. We have to look at our chart, which is in my notes. Here we go. around the sulfur, we have 6 regions of electron density participating in bonding. For 6 regions of electron density, we would have an electron pair geometry of octahedral, where all angles are, I think that says 90 or 100 degrees. It's kind of hard to read. Octahedral. Let's check our answer key. 91A. Both the electron geometry and the molecular structure are octahedral. Cool. And we can say that because all of the electrons contributing to this shape are participating in bonding, and there are no lone pairs. So they are same. If there were lone pairs, as I'm sure there will be on one of these, we would get a different electron geometry. So this is kind of the flow, right? You account for all of your electrons in bonding or as lone pairs. You make a best guess with your Lewis structure and then test the formal charge of each of the involved species. If you have a positive or a negative formal charge on something that is not appropriate for that molecule, then you go back to the drawing board. You start moving electrons around. You have to redo your accounting to make sure that all of the electrons are accounted for, and then recalculate your formal charges. Once your formal charges match the charge of the molecule overall, then you're good. You can start looking at your geometries, and you just have to use that chart, really. I mean, you can memorize some of them. Some of them will be really, really common. Common enough that you should be able to recognize them. This is a trigonal planar molecule. Trigonal, 3 angles. Planar because everything around this carbon is on the same plane. There are no other regions of electron density to contribute to that. Right. That's not one of the examples, but it was one that I had ready in my head. We'll look at example D, which is CH3 with a positive charge on it, right? You have your central carbon. We have 3 hydrogens bound to it. We know that well, you can't see that. Let me move it. Okay. We know that carbon would normally have 4 valence electrons, but one of those is missing to account for that positive charge. It couldn't be missing from one of the protons, from one of the hydrogens. And so 2, 4, 6, we could have 7. There's our 1 electron. Let's do our accounting. Carbon has 4. Each hydrogen has 1, gives us 3, would be 7. We're getting rid of 1 because of that positive charge. Gives us 6. 2, 4, 6. So that all of them would be accounted for participating in bonding. Cool. Glad I did that accounting step because I would have made a mistake. Fantastic. Now let's do our formal charge calculation. Remember that we're looking for a positive 1 charge. On that molecule, and we have it in this configuration. Now, as far as geometry, we don't have any regions of electron density from lone pairs. We just have, I'm going to do this in red, 1, 2, 3. Oh, gosh. Excuse me. 3 regions of electron density in those bonds. I'm pretty sure this is a trigonal planar molecule, but let's open up my notes to find out. We have three regions of electron density and no lone pairs. So trigonal planar, all angles are 120 degrees. I want to find that other chart. Here it is. Regions of electron density, no electron pairs. That would be trigonal planar. Cool. There you have it. We have a couple minutes left. We can just do this first one. Um, question 94 and 98 are related to each other, so we can kind of do them at the same time. We want to predict the electron pair geometry and the molecular structure of each of the following ions, and which of the molecules and ions contain polar bonds, which of these molecules and ions have a dipole moment. Resonance structures and polarity are related to each other. If a molecule has a resonance structure, it has polarity. I'm pretty sure. Looking at our first one, we have an oxygen surrounded by three hydrogens and a positive charge. I'm just going to look at our formal charge here really quick. We have 6 minus 0 minus 6 equals 0. Six, 7, 8, 9, 2, 4, 6, 7, 8, 9. All right, fine. Number of electrons. There's 6 accounted for. We need 3. We get rid of one of those because we have a positive charge, and we have 2 to account for. Oxygen has a lone pair on it. So we have 4 regions of electron density. 1, 2, 3, 4. And we have a positive charge on the molecule overall. Okay. Predict the electron pair geometry. 4 regions of electron density gives us an electron pair geometry of tetrahedral, but we have lone pair, so our molecular geometry is trigonal pyramid. So trigonal pyramid, I'm going to draw this a little bit differently. Wedges like this are off the plane of the paper, so that's angled towards us, and dashes are into the plane of the paper, away from us, and a line is on the plane of the paper. We have our lone pair also on the plane of the paper. So this is why we say this has a pyramid. Let's see, how do I? Because it has this rough shape, the oxygen at the top and its lone pair, and the hydrogens. Now, if I were to draw, oh, be backwards, the overall polarity of this molecule would have a positive charge around where the hydrogens are grouped and a negative charge localized around that lone pair. Because they are electrons, they have a stronger negative charge than do the protons bound to that oxygen. So which of these molecules and ions contain polar bonds? H3O plus has a polar bond. Negative charge is localized around the oxygen's lone pair. Positive charge is localized on the opposite end where those hydrogens hang out. This is a really good example. I like this one. Because if I had just drawn this and not accounted for that lone pair electron, you might say that this is trigonal. Yeah, you might say that this is trigonal planar, and you would be wrong. Doesn't exist. I really, really like that example. Let's look at, ooh, excuse me. We're a little bit over time, so if you need to jet, I understand. I'm going to work through at least one more of these because I have a little bit of extra time, and I want you to see at least one more of these. So if you're watching the recording, stick around. Fast forward through it. Let's see. Yeah, all right. We're going to do xenon tetrafluoride. Xenon is a noble gas. It has 8 valence electrons. Fluorine, we've got 4 of them. Each has 7. Gives us 36 total to account for. Now, we already know that those fluorines are going to be unhappy with anything other than a single bond. So we're going to go ahead and draw these in. We have 2, 4, 6, 8 participating in bonding. And we have 12 times 4 is 20, excuse me, 6 times 4 is 24. Leaves us with 4 electrons to account for. Xenon is in group 3 or above, so it can be hypervalent. Yes. So we give it 2 lone pairs. That accounts for all of our electrons. Let's calculate formal charge. Fluorine is easy. We've done this enough times that we know each of those has a formal charge of 0. Xenon, we started with 8. We have 4 lone electrons and 4 bonds, so a formal charge of 0. This Lewis structure is valid. What on earth is our geometry? So our electron geometry, we have, I'm going to circle these, 1, 2, 3, 4, 5, 6 regions of electron density. Going back here, that would give us octahedral. But we also have those 2 lone pairs. That puts us here. This would be a square planar molecule. We said that would be octahedral, and our molecular geometry is square. Did I say square planar? I said square planar. So to draw this, I think it is worthwhile to do this. We have our xenon in the middle. I'm going to say we have our lone pairs on the plane of the paper above and below that molecule. Then we have, coming out of the plane of the paper towards us and at an angle, two fluorines. And then we have going into the plane of the paper and away from us, four fluorines. The fluorines, if we can visualize this in space, the fluorines are all on the same plane. Like if this is a disk, the fluorines are all on that disk, and the lone pairs are on the top and the bottom of that disk. So is this polar? This would be nonpolar. We have a, I'm confident in my answer. It was pretty reflexive, but I want to be 100% sure. Yeah, this is a nonpolar molecule. Because xenon tetrafluoride has a symmetrical geometrical structure, square planar, the dipoles across the xenon fluoride bonds cancel each other out. So if you can imagine, yeah, I'll do this in red. The fluorine would be more, would it be more electronegative? Let me grab my periodic table here. Electronegativity. Fluorine is way more electronegative than xenon. Xenon has its full octet. It's super happy. It doesn't need more electrons. Fluorine really, really wants to get from 7 to 8 valence electrons, and so it's greedy for electrons. And so we're going to do these on dashed dotted lines and wedged arrows. There's a general positive towards the xenon and a general negative out towards the fluorines, but they all cancel each other out because they're all at equal angles to each other and on the same plane. Similarly, you have these two regions of electron density, north and south poles of your xenon, that cancel each other out as well. So this would be a nonpolar molecule. Okay, that is all I have for you. Thank you all for your time and attention. I understand your final exam is next week. Best of luck. And I hope to see you all next term for Chemistry 222.